For our next example, we consider a solid, infinite cylindrical conductor of radius a with uniform linear charge density lambda. We can use Gauss's law to determine the electric field outside this cylindrical conductor. Since the charge must be distributed uniformly on the surface of the cylinder, we know the magnitude of the field produced by this charge can only depend on r, the two-dimensional distance from the axis of the cylinder, and its direction must always be perpendicular to this axis. To find the value of the field, a distance r from the axis of the cylinder, we choose our Gaussian surface to be a cylinder of length L and radius r centered on the axis of the conductor. For the two end surfaces, E is parallel to the surface and therefore perpendicular to dA. Consequently, E dot dA over the ends is 0. Therefore, the only contribution to the integral of E dot dA over the cylinder comes from the barrel surface. We know the direction of the field must be perpendicular to this surface, and the magnitude of the field must be the same at all points on this surface. Consequently, the scalar product E dot dA just becomes the arithmetic product E times dA, and we can once again take E outside the integral. The left-hand side of Gauss's law then becomes just the product of E and the surface area of the barrel. The right-hand side of Gauss's law is, as always, the charge enclosed by this cylinder divided by epsilon naught. In this case, the charge enclosed is just the linear charge density lambda times the length L of the Gaussian cylinder. Therefore, the electric field outside the charged cylindrical conductor is just equal to lambda over 2 pi epsilon naught r. We see then that the field outside a charged infinite cylindrical conductor is identical to that produced by an infinite line of charge with the same linear charge density. This result is not a coincidence. Since both of these charge distributions have cylindrical symmetry, the field at a distance r from the axis of symmetry is totally determined by the charge enclosed by a cylinder of radius r. The same charge enclosed, the same field. This situation is just like that of our original example, in which the field outside of the solid insulating sphere was found to be equal to that of a point charge located at the position of the center of the sphere. The same charge enclosed, the same field. We'll now move on to the remaining symmetry, that of an infinite plane of charge.